as I said, welcome to you all. It's great to have you all here, and we're delighted that you could join us. My name is Liz.
And I'm Charlie.
And we are members of the NRICH team based here in Cambridge in the UK. We must say thank you, first of all, to Trinity College here in Cambridge, who fund these webinars so that they are free to you as participants. If you wouldn't mind turning off your cameras, please, that would be really helpful. So some of you may have joined our webinars before, and so you may be aware that actually this webinar is the fifth one in a series. And I'm just going to share the NRICH website with you. So just to give you a little bit of an overview of where we've got to. So here is the NRICH homepage, and the webinar series that this is part of, what we've been doing is we've been focusing on helping you as practitioners develop students' mathematical thinking. So Charlie, if we go to the secondary teacher landing page here, we'll be able to get a bit of an overview of this webinar series.
Can we check that everybody is seeing the secondary teachers page?
Of course, yes. Could you, yes, you
Tom.
can, Tom. Thank you, Tom. Brilliant. So here we've got, this is our secondary teachers landing page, and this second box here helps you, if you are particularly interested in developing students' mathematical thinking, this is the place to click, and we'll say a bit more about this later. Just to give you a little overview, this reflects, these 5 stages that we've focused on so far reflect the process that you might go through if you're faced with a problem and you're tackling a problem. So our first webinar was all about supporting students as they explore and notice, leading into a more systematic way of working, which in turn might lead to some conjecturing and generalizing. Then to make sense of what we found, we may draw on some visualizing and representing, which brings us to this 5th webinar, which is focusing on reasoning, convincing and proving. Now, in fact, actually, today is going to be slightly different to the previous 4, because although we are very aware, of course, that coming to that 5th stage in that process, convincing and proof is really important, and that is where we might be ultimately aiming for, actually, reasoning is all pervasive. So what we're going to do in today's webinar is, first of all, we're going to help you, we're going to draw attention to the opportunities that rich mathematical tasks offer for doing lots of reasoning in the moment in your classrooms. And then we will give you a few examples of that sort of final 5th stage of the more formal proof. So Charlie, shall I hand over to you? And you've thought about the tasks that we're going to be working on.
Well, could we go back to the secondary teachers page? So on the left hand of the menu, we've got teachers. Oh yeah, sorry, you're the secondary teachers. On the left hand, we've got all the problems linked to the curriculum, which is what we've been doing for some time. And let's imagine we want to do some work with students, getting them to add and subtract positive and negative numbers. Okay. So we might go to curriculum linked problems and look at our mapping document. Yeah. So we'll get, it's currently organized like this into 4 sections: number, algebra, geometry and statistics. And since we're going to focus on number, let's scroll down to number operations and calculation methods. And here towards the bottom, right at the bottom of the first column, we've got a problem called Connect 3. Yeah. Let's have a go at Connect 3. In this problem, you've got 2 dice or 2 spinners. One's got the numbers 1, 2, 3, -4, -5, -6, and the other one has got -1, -2, -3, 4, 5, 6. And we spin them, and we then can add the scores on the 2 spinners, or we can subtract one from the other. Okay. And once we've done that, that value, we put a counter on the board. Okay. And then in this case, the default option is we're playing against a computer, but there are other options available. And then the computer will have a go, and we'll take it in turns to have a go. And eventually the winner is the one who gets 3 in a row.
Okay.
And a row can be either horizontal or vertical or diagonal.
Right.
So let's
So we're
spin
going to
away.
go first, I think, aren't we? So we'll spin. Let's see what numbers we end up with. Okay, 3 and -3.
So can you just show us? Yeah, so you can drag both of them down. And call it plus if you want.
Yeah.
Or you could subtract -3 from 3. Or if you swap the numbers around, you could subtract 3 from -3.
Okay.
So I'll do the easy one. The addition, 3 plus -3 is 0.
Okay.
So
we could choose to place the counter here.
We could choose to place counter here. But if we have -3 and take away 3,
yes,
we'd get -6.
-6, so that's another option.
Or 3 subtract -3 gives us 6.
Yes. So those are our 3 options. So we've got -6, 0, or 6. And so I guess we're asking students to decide where we might place the counter.
Yes.
Okay.
So perhaps a good strategy is to place the counter on a cell that belongs to as many winning lines as possible.
Okay.
So here's a challenge for everybody.
Yeah.
If I place the counter on the number 6, could you write in the chat how many winning lines could include the cell number 6? Okay. And the winning lines can be horizontal, vertical, or diagonal.
Right.
And we'll do some working out at our end as well.
We'll have a go as well.
There's already some disagreement.
Yeah, that always makes more interesting conversations when there's disagreement.
Okay, I'm going to repeat the question. If we were going to go for 3, take away -3, the answer would be 6. We want to work out what the merits are of putting our counter at 6.
Yes.
And we might judge the merits of that by thinking about how many winning lines contain the number 6.
So how many winning lines of 3 contain the number 6?
Thank you.
Yeah. So we've still got a little bit of disagreement, potentially. We can go horizontally, vertically, and diagonally, just to be clear. What do you think then, Charlie?
Okay, I think 7 is correct.
Yeah.
And the reason is this. I think there are 2 vertical lines which contain the number 6, because the 6 could be in the middle of a line of 3, or it could be at the bottom of a line of 3.
So that's 2 vertical.
So likewise, there are 2 horizontal lines. One of them contains the numbers 5, 6, 7, so 6 is in the middle, and one contains the numbers 4, 5, 6, so 6 is on the far right.
So another 2 makes 4.
Diagonally, from top right to bottom left, there is only 1.
Yes.
That starts at 2 and finishes at 10.
So now we've got 5.
But the other diagonal could start at 12 and finish at 0.
Yeah.
But could also start at 6 and finish at -6.
Agreed.
So there's a pair. Now the question is that a better option than going for 0? Often one thinks that going for the middle is the best option.
Yeah.
So would everyone like to have a go at working out how many winning lines are there that contain 0? So a winning line's got 3 numbers. How many winning lines are there that contain 0? There's much less disagreement now. Great. And again, there's a chance to work systematically by thinking about, oh, look, there are 3 vertical lines, there are 3 horizontal, there are 3 diagonals that go from top left to bottom right, and 3 that go from top right to bottom left. And so it looks like 0 is the place to go to. And we're just mentioning this game because the students are thinking about adding and subtracting negative numbers, being interested in looking at the different results that are possible.
Yeah.
So Colin Foster talks about purposeful practice.
That's right. Yeah.
So they're doing the addition and subtraction that we want them to rehearse, but at the same time they're having to think strategically and make informed decisions.
That's right.
They're not just randomly having a go, because if they do it fairly randomly, they'll lose against the computer most of the time.
Yes,
exactly. Okay, so
that's a really nice example of a game where those little bits of reasoning, are relatively easy to get to.
Yeah,
easy to incorporate.
You sort of want to milk the problem for all the opportunities they have for mathematical conversations. Now, I'm aware that we've selected 10 problems to talk about today.
Yeah.
Which means that we've got about 4 minutes per problem. So apologies to everybody if we're rushing through the problems, but we're hoping that dipping into them will give us an opportunity to just draw attention to the kind of mathematical conversations that are enabled by some of these problems.
Absolutely.
So let's move on, and let's imagine...
We're going back, we're back to the mapping document again.
Back to the mapping document, and let's stick to number.
Okay.
And let's imagine that we want to do some work on factors and multiples.
Right.
There's a section here in the mapping document.
There we go.
Factors and multiples. And one of our favourite problems is the factors and multiples game.
Yeah, this is a lovely one.
So again, so in this case, we've got a nice interactivity, and one of the challenges is to make a nice long chain.
Yes.
So we could be working collaboratively on this.
Yeah.
And to make a chain, you have to follow any number in the chain by either a factor or a multiple of the number that came before.
Okay.
So we could be doing this together, and let's imagine we start with 40, and then a factor of 40 is 20, and you can just click on it, it'll go, and then a multiple of 20 is 100, and a factor of that is 50, and then you could go for 25 and 75 and 3 and 33 and 99, and you can see we've done this before, and 11 and 66.
Well, I can't keep up with you.
And
yeah.
And we could have a go, and this would be a lovely challenge.
And longer. And so the green here, Charlie, is giving us an indication that actually we are following the rules correctly.
Yes, if you clicked on 7, for example, now, which is not a factor of 66, it would tell you.
Right, it's not.
But you could put it back.
Okay.
And also, if you got stuck at 66 and didn't know where to go, but you realise, oh, I haven't used the 10 and it could have gone before the 40, you can nudge the 40 to one side by dropping the 10 in its place, and the 40 will move.
Lovely.
So let's try that again.
Start from scratch.
No. Okay, and
so
for example, the 5.
So the 5, well, we can put the 5, I mean, it doesn't really matter, does it? Let's put the 5 over the 10.
Yes.
Okay.
But you could also not only nudge the first number out, but you can also nudge numbers in between. So, for example, the 2 could go between the 20 and the 40.
Right.
So you want to nudge the 20 out of the way. So you drop the 2 on the 20, and you can make a long chain.
Fantastic.
So, nice long chain. And I mean, I'd be very happy if students managed to get chains of over 50.
Yeah.
But it is possible to have chains of over 70. The longest possible is 77. So I can imagine displaying the longest chain so far and leaving that for students to figure out. And I think a strategy where you're sort of a bit like table tennis, ping pong, you go from big number to small number to big number to small number, because the big numbers don't have multiples available, but they do have factors. And if you want to, otherwise, and what happens is often students use all the small numbers that they know really well, say the numbers from 1 to 60, and all the big numbers get left behind. So there's a lot of reasoning here as well as
all that fluency. And there is like a competitive game you can play as well, Charlie, isn't there, linked with this, as well as that cooperative challenge. So if we just refreshed, just to give ourselves. And in this game, we could take it in turns to choose a number, which is either a factor or a multiple of the number that your opponent has just chosen. But the aim of the game is to prevent your opponent from being able to make a move. Now, actually, I mean, I'm talking as if we're playing against each other, but actually it's nice to get a pair and a pair playing against each other, isn't it?
In a lot of these problems, getting students to work in pairs encourages conversations where they have to articulate their reasoning. So not only depending on conversations between the students and the teacher, you want to encourage as many mathematical conversations between the students as possible.
So I wonder whether we could have some suggestions on the chat. If you were going to be going first in this game, what number might you choose if you wanted to try and prevent, ultimately your aim is to prevent your opponent from being able to go?
Yes, what would be your starting point that could guarantee a win?
Could guarantee straight from the beginning.
Yes.
Yeah. Perhaps you could suggest. Okay, we've got one suggestion. Another. I think those two have got something in common, but okay. So some of you are saying prime numbers. Some of you are being a little bit more precise. So Charlie, if I chose, I mean, I happen to know that 13 is a prime number. If I chose 13, what would you do?
I might choose 26.
Oh, okay, yeah. And then I choose, well, there are so many options.
You could choose 2, you could choose, I could choose 40, and then we'd often...
Okay, that's not what I was hoping. Okay, we're getting some slightly more nuanced contributions. So we've had some suggestions. A prime number bigger than 50. That's nicely expressed.
Andrew has suggested 97. What would you do, Andrew, if 97 is not available for some reason? And Shivangi has suggested 73 and 97.
Yeah, okay.
Be interested to know what these numbers have in common. Well, let's imagine, Liz, that you were playing against me.
Okay, yeah.
Okay, so why don't you start with Shivangi's suggestion?
I'm going to start with 73.
Yes.
Okay, what are you going to choose?
Do you want to do it on the screen?
Yeah, okay, let's do it on the screen. 73. Right, what are you going to choose, Charlie?
Well, I can't use a multiple of 73.
Absolutely.
And the only factor available to me is 1.
Because it's a prime number, absolutely. Okay, so now I am going to choose, if I went with Shivangi's suggestion of 97.
But let's assume 97 is not available. For some reason, it's not working. Could you choose anything else?
Yes, I could choose another prime number, and as long as it's bigger than 50, I'm fine, because the only number you can't then, because you've already used 1.
But do you know any? 91.
I think you're trying to trick me, Charlie. I think 91 is a multiple of what? 13, is it?
Yeah, 7 13s.
Tom's helping me out. 89. 89. There we go. Charlie.
Okay. The only factor 89 has is 1. And 1's been used already, so it can't be used again.
Okay.
Okay, so here's a lovely example. Again, we can get students thinking about factors and multiples, rehearse their factors and multiples, think about the rules, but at the same time, they have to think strategically.
That's right.
And we've worked with a colleague who often talks about giving students activities which require them to make choices.
Yes.
And in Connect 3 and in Factors and Multiples game, they're having to make those kind of decisions. And if they're working in pairs, for example, then they need to articulate their reasons for choosing one thing as opposed to another. And that offers opportunities for mathematical reasoning and
absolutely.
Right, 4 minutes.
I think you wanted to draw attention to one other problem in that. Ooh, it's very big. That's because I made the screen big for the game. There we go, that's better.
Oh, yes.
Should we quickly look at dozens? Now, this is in the same cell, so it's addressing the same parts of the curriculum, but this is a lovely opportunity for reasoning.
Okay, so
shall I choose multiple of 6?
Yes, so yes, this is not the default, but
no.
We'll choose multiples of 6 as the starting point, and you've got to choose you've got to use the numbers that have been offered to you, which are the 6 and the 4,
Mm-hmm.
and then you've got complete freedom as to what your other number could be, what other digit to use. Mm-hmm. It can be a 6 or a 4 if you want to.
Yeah, you could repeat.
And you're trying to make a 3-digit multiple of 6.
Yes. Okay. So I wonder what we might do. We've got some suggestions.
Oh, and I didn't mention, it's got to be the largest.
That is quite crucial. Yeah.
I was going to try and catch you out.
Okay. Well, I get Tom is giving me a helping hand again. I think I know that a multiple of 6 has got to be an even multiple of 3. I guess the 6 and the 4 add to 10 already. And so I think the largest digit I can add and still be a multiple of 3 is an 8, because that'll give me the digit total of 18. And so in order to make that as large as possible, I'm going to put the 8 here, the 6 10s and 4 1s.
If you hadn't done that and you'd written 8 4 6,
good idea.
Shall we just see what the computer says?
Oh yeah, that's a good idea. That's a good idea. And we can show you.
So you're still using the numbers, and it's telling you you have got a multiple of 6, but there is a larger one.
Yeah.
Yeah.
So this is an example. Many of our interactivities do this. They've got inbuilt feedback for students without giving away the solution, but they're encouraging that little bit of resilience, I guess, and perfect opportunity to use some mathematical reasoning. Again, with factors and multiples. Okay, so should we go back to the mapping document?
Let's look at something in algebra.
Okay, yeah.
So at the top there, and let's look for functions and graphs.
Okay.
Do some work on coordinates.
Nice, right. Functions and graphs. Here we go.
And let's go for the treasure hunt. So in this case, there's a treasure hidden at one of the grid points on a 12 by 12 set of axes. You've got to try and find the treasure.
Okay.
You type in some coordinates, and it's going to tell you how many steps away you are, or how many blocks away. You're not flying as the crow flies, but along a horizontal grid of streets, like a New York map, where you can only go horizontally or vertically.
Okay, so I'm going to put in a point to test. Well, I don't know, somewhere near the middle, maybe. I'm going to go for 6 5. Okay, test those coordinates.
And you're 5 away.
5 away. So that could mean, for example, I was 1 2 3 4 5. I was up here. If I click here, I'm going to get a little mark to remind me. I could be one horizontal and 4 vertical, for example. So I think I might be able to mark
2 across
2 and
3 up.
3 and 2, 4 and 1, 5 and 0, and then similarly 4 across 1 down. And I think if I do this, I'm gonna. That's right. And then this here would be
exactly 4.
Then. And then, oh, this looks interesting, Charlie. I'm getting quite a nice shape here. So these are all 5 away.
So if it was with a compass, you'd get a circle. But sometimes this gets referred to as taxi cab geometry
on the grid.
And you get a square.
Nice.
So where's your second choice?
So I guess it makes sense for me to choose one of these points as my second choice, because you never know, I might get it right first time. Oh, well, I'm going to choose this one. So I'm going to go for 6 10. Let me go for 6 10, and the computer will give me some feedback about how far away I am this time. Only 2 steps away this time. Okay. So I think I've now narrowed it down to these 2 points, because there is. So now, well, I want to choose one of those, but it doesn't really matter which one. Shall we go for 7 9? 7. Oh no, I didn't even write 7. 7 9. Oh, okay, so I think I know now. Here we go. 5 9. Yay!
So you did that in 4 guesses.
I did.
But it is possible. Ooh. There is a strategy for always doing it in fewer than 4 guesses.
That's tantalizing, isn't it?
So not only is there a chance to practice coordinates, but there's also a chance to think strategically about where to look for the treasure.
Okay.
So again, shall we give everybody a chance to put something in the chat?
How could you have been more strategic than me there? any suggestions?
Sorry.
Okay, we've got one suggestion about what we could do, a starting point. Anybody like to contribute anything else?
I'd quite like to try Francesca's method of two guesses being at opposite corners.
All right. So let's try our new game.
Go for 0, 0 and 12, 12.
Okay. Okay, I'm told 12 steps away.
Okay. And then type in 12, 12.
Okay.
So I think all the points along the diagonal going from 0 to 12 to 12, 0. But I'm not sure I'm going to be able to. I can't guarantee that my next one is going to. So I think, Francesca, you're going to need possibly 4 goes. So I think we're going to leave it at this and let everybody think about it.
Let you think about that. Yes.
And we're going to move on because otherwise we're never going to get through all the problems. But here's yet another example of mathematical reasoning, thinking. We want this to be at the heart of mathematics lessons, where students are having to justify the choices that they make.
Yeah.
Okay.
So you can really make the most of all the opportunities to reason.
So could we scroll to the top of the mapping document again?
Yeah.
We haven't, okay, can we look at algebra again?
Yeah.
Equations and formulae.
Okay.
And I want to get students thinking about simultaneous equations.
Okay, yeah.
So one problem that we have here is called what's it worth? So some of you may have seen this already because we might have mentioned it. And in this problem, you've got this grid and you've got some squares and triangles, hexagons and circles, and each of those symbols has got a value. And you're told that in the top row, the value of the 4 symbols add up to 28. On the second row, they add up to 30. And likewise for the other 2 rows, and likewise for the columns.
Yep.
The last column will add up to 22. And you've got to work out the value of the symbols on the left-hand column. And a lot of students go about this in a fairly random, haphazard way, testing different ideas out and eventually hitting the answer with trial and improvement. And there's great value in doing that.
Yes.
And if you came to our Exploring and Noticing webinar, you'll know that you can be fairly systematic and you can gain knowledge as you after each go.
Yes.
But we also want students to be efficient and find elegant ways of solving a problem like this. One of our colleagues used to talk about to be a good mathematician, you need to be a good mathematical detective.
Yes.
And so the question is, you've got many more clues on this grid than you need. So what we've done is we've highlighted certain bits of the, bits is a terrible word, of the grid. So Liz.
Yes, okay.
If I said, I only want you to look at the top row and the second column, what could you deduce just from that?
So I think from this top row, I know that 2 squares and 2 triangles add to 28. So I think, therefore, that if I halve that, I know that 1 square and 1 triangle adds to 14.
Yes.
So therefore, I know that the square and a triangle in this column adds to 14. So if I take away 14 from 30, I'm left with 16. So I know that 2 squares has a total of 16, so 1 square is 8.
And once you know what 1 square is, you can work out the rest.
Yeah.
Okay, let's look at image 3.
Okay.
Could you do something similar?
I'll try. All right, so this time I think, again, I can use the knowledge that a square and a triangle adds up to 14. I think this time I'm going to have to add these 2 rows together. So I'm going to get a total of 38. I know that a square and a triangle adds to 14. So if I take away 14 from 38 leaves me with 24. So I know that 6 circles add to 24. So I know that 1 circle is 4.
And once you know the value of 1 circle, you can work out the triangle and you can work out the square. And this feels much more efficient and elegant than trial and error.
Yeah.
Okay, come on then. I'm going to give you a harder one. Image 5.
Yes. Okay. Right. Image 5. Ooh, this feels a bit different. So I think here we have got the difference between this column and this column is only the top shape. So the difference, they only differ in their top shape. So similarly, here, these 2 rows differ in the same. So I think that this is telling me that a square is 2 more than a triangle if I compare these 2 totals along the 2 bottom rows.
Yeah.
Which means that if I know that this column is 23, I know that this column is going to be 2 less than that, which is going to be 21, because I know that the only difference between the 2 columns is the square and the triangle is 2 less than the square.
So you haven't had to work out the values of any of the symbols.
No, that's a bit different.
And you've still been able to work out, answer the question that was asked.
Right.
Come on then. Shall we give image 6 to everybody to think about? Okay, so we're offering you image 6. What on earth were students thinking about when they just looked at this information and figured out the answer? Okay, and so some people have noticed that if you sum the rows, the 28 and the 30 and the 18 and the 20, that all adds up to 96, which must be the sum of all 16 cells. But we could have added the values of the cells by working vertically, and the 30 and the 23 and the 22, the values of the 2nd, 3rd and 4th column all add up to 75. And if the whole lot must add up to 96, there must be a 21 missing.
Yeah.
And I wish I'd thought about that.
I wish I'd thought about that too. Yeah.
And I think I want to introduce students to the possibility, I think we want them to be resourceful and see that there are alternative ways of solving problems like this.
That's right.
So we give them choices because there are different strategies they can use, and they need to decide which strategy is best.
Yeah.
At the bottom of this problem is a link to Fruity Totals, which is also on the mapping document. And teachers have said to us that after working on that problem and on Fruity Totals, their students are in a much better position to tackle simultaneous equations.
Right.
Now, in the teacher's resources, so for the problems of the mapping document, there's always the teacher's resources. And in this case, we've suggested some possible starting points. So you can sort of program the interactivity so it gives you the combination of fruit. So this works just like the previous one. So you can go to the cog.
So I've copied that code that was in the teacher's resources, and I'm now going to replace the existing code with that one. I just need to click to make sure it goes pinky purple. And then I'm going to say, yes, take effect in this current window. And this is the starting point that the teacher's resources suggest. It provokes good conversations.
And it's fairly easy because you can see very easily that on the far column, you've got two, they're supposed to be damsons. And the idea is that we've got A, B, C, Ds, apples, bananas, cherries, and damsons. But Liz and I call them plums because
they look more like plums. Maybe that's a scale issue as well.
So yes, again, yes, 2 apples and 2 damsons add up to 26. So you can work out one of each, and then you can look at the bottom row.
Yeah.
And you can do similar reasoning to the one
that we did
earlier.
Yeah.
And so those 2 problems combined. And if you go to the cog, you can make the problems slightly harder.
Yeah.
There are levels 2, 3, 4, and 5. And they don't look like simultaneous equations in terms of the algebraic, but the kind of thinking that's required is exactly the kind of thinking that you would want students to be doing when they're manipulating equations to solve simultaneous equations.
Yeah.
So that's also in the mapping document.
Yeah.
Okay, we haven't done any statistics, Liz.
No, let's
Shall we go
then.
to
so we're back at the mapping document. I presume we need to be in a different tab, statistics and probability. And which problem would you like to have a go at here?
Shall we have a look at M, and M?
M. Okay. Right.
So I wonder whether, yes, okay. We're being asked for 5 positive whole numbers. We're not going to be using zeros. And we're told that the mean average is 4, and then the median and the mode are both 3.
Okay.
So perhaps a minute on the chat where you can type up a possible solution.
A possible set?
Yes.
Yeah. Okay. Yeah, that's a good starting point, Tom. Yeah, agreed. If we know the mean, we know there are 5 numbers in total. We know that they sum to 20. Yeah. So if you could post, a possible set of 5 positive whole numbers that satisfy those criteria, that would be fantastic, please. Okay, great. Got a couple of possibilities. I'm going to just stop sharing the screen now. So just to remind you, mean 4, median 3, mode 3. I'm going to instead now share the visualizer we've got here. Charlie's going to do a little bit of scribbling. Oh, no, sorry, there we go. Okay, just need to move a bit.
Okay, so hopefully you can all see my sheet.
Thank you. Thanks for confirming.
So I was working with some students who I hadn't met before, and they were there with their teacher, and I set them this problem. And the teacher had never seen this problem before. So he was sitting on the side, he's standing on the side of the classroom with a notepad, and he was having a go at the problem himself. And I never got to see what he wrote, but when we were coming to the plenary session and we were trying to check that we had all the solutions, which was the challenge I set them, I hoped that the teacher had been quite systematic about this. So I took his pad of paper, I took the risk, and I wrote down on the board what he'd written. And he'd written 1, 2, 3, 3, 11, followed by 1, 3, 3, 3, and 10, and 1, 3, 3, 4, and 9. And then I said to the students, I think your teacher has got a system here that guarantees that he'll find all the possibilities. What do you think he wrote next? So I'll ask you that question. What do you think the teacher wrote in the next row? And somebody has suggested 13358, and that is indeed correct. What about the next row? Now comes a tricky one. What did he write next? I think 23357. Is that what came there? Yes. Yeah. But somebody has suggested 2, 2, 3. Okay, so Francesca suggested 22334. I'm not going to allow bimodal, so yours has got 2 modes. So
good to clarify.
And actually, I'm not sure the mean is 4 either. So we'll just have 1 mode. Okay. So Tom's 23357, I think, went there. I think there are a couple that come before. Okay, and Shivangi suggested 23348. And I'm still
You've got a mysterious
waiting
gap,
for
Charlie.
The one that came after 13367. Okay. Now, I want to clarify, this is not the only way of being systematic. No. There are other ways in which you could do this. Yeah. But this happened to be what the teacher did. And it was a really lovely example of how a teacher approached this in a way that could guarantee that he found all the possible solutions. Yes. And so he was a real good model for the students. And
you took a risk then.
I took a risk, and it worked. So I was really pleased. Yeah. And again, a chance to work on averages, but also work on being systematic, which seems like a really important skill. So again, it's about having to make some choices, and maybe you do this in a pair, and you have to justify to your partner why you're doing what you're doing.
Absolutely.
And actually, there are other ways of organizing this. And one way is, for example, saying, well, I need to have at least 2 3s. So I could have 2 3s or 3 3s or 4 3s. Yeah. I can't have 5 3s because the mean won't be 4. Yeah. But let me find all the possibilities with 2 3s, all the possibilities with 3 3s, all the possibilities with 4 3s. And again, as long as one is systematic and can one explain why one has got all the possibilities, that's fantastic.
Yeah. Okay, I'm going to stop sharing the camera, and should we go back to the website?
And let's go back to number.
Yeah.
A lot of the work that we've been doing has been for slightly younger students. So let's look at a problem that we might do with some slightly older students. And this is a problem, again, in the number operations and calculation methods. In the 4th column, we've got a problem called slick summing. Now, we're very taken by, and we can't remember who introduced us to this idea, but the idea only doing for students what they cannot do for themselves. Yes. So we've got a video that we're going to show you, but there's no sound, because we think that what I'm writing on that sheet of paper is sufficient for students to figure out what's going on. Yeah. So we could go explaining what's going on, but instead we want the students to figure it out for themselves. Yeah. So we'll just play this video. Don't worry about playing with your volume controlled.
There is no sound.
There is no sound. The problem is called slick summing. I'm sure you know what's going on there, so I'm not going to elaborate, but I could imagine using this with a class and asking them to turn to their neighbor and explain what's happening. And then we've got a range of problems below which asks students to use that kind of strategy for adding all the numbers from 1 to 20, or adding all the even numbers from 2 to 20, or all the even numbers from 42 to 100 and so on. So adapting that. But this idea that they can they can be introduced to something without having it explained and then having to make sense of it is good.
Absolutely.
Right, we're going to finish off by thinking about these problems that Liz was talking about, where we start with the exploration section, we go on to conjecturing and generalizing, and finish with generalizing and proving. And there are two problems in particular that we quite like. One is tilted squares. So if we go to geometry and go down to, where do we go? There, I've just seen it.
Thank you, here.
Yes, so I think that's in the section to do with Pythagoras.
Angle facts to Pythagoras, yeah.
I'm going to steal your mouse, so that's okay, Liz. So in this problem, students are encouraged to think about, well, we possibly rehearse what is the area of a 2 by 2, a 3 by 3, a 4 by 4, 5 by 5 square. And once we've verified that they can work that out, we ask them to work out the areas of tilted square, perhaps by boxing in the square and working out the area of the box and taking away the area of the 4 right angle triangles that they don't want. And they can then they normally work out that the area of that is 5. And when you go 3 across and 1 up, the area is 10. And when you go 4 across and 1 up, the area is 17. And then 26. And then 37. And then they start noticing that all these numbers are one more than a square number. And they might then go to a more tilted square. So 2 across and 2 up, and then 3 across and 2 up, and 4 across and 2 up. And when they work out the areas of these by boxing the shapes in, they find out that the area of the square is always 4 more than a square number. And they start making some deductions and conjectures, and eventually come up with Pythagoras' theorem. Now, that is not the end of the journey.
Right.
So it'd be quite nice if the students could also prove that this is the case.
Yes.
That if you have a distance of A along the bottom here and B to go up, the area of this square is going to be A squared plus B squared. And students might have difficulty doing this. So we have got a proof sorter.
Yes.
So can we go back to the mapping document?
Yeah.
And right next to, in the same box, we've got Pythagoras proofs. Now, students can work out, well, students who we're doing Pythagoras with may have come across the idea of boxing in, which is how they've been working out the area so far. So it can work out that the area of the big box is a plus b all squared. The area of each of the right angled triangles is half AB. So the area of the blue square is going to be a plus b all squared minus 4 lots of half AB. Yeah. And deduce that that's going to be a squared plus b squared. But they may not come up with this independently. Yeah. And I don't want to just show it to them. I don't want to do all the thinking for them. So in that spirit, what we've done is we're offering a proof sorter where elements of the proof are all mixed up. Yeah. They're like on cards, and students can move them around and put them in the order that they think is correct. And then, and I'm just doing this randomly, but eventually, once they've got them in an order that they're satisfied with, they can go and they can submit their solution. Yeah. So again, this feels like we're not doing all the work for the student. Yeah. We're introducing them to the kind of rigorous mathematical thinking that we expect, and we're presenting it in a form that introduces them to more rigorous proofs. Yes. Likewise, we have a problem. Can we go back to the mapping documents? Yeah. And very quickly, cyclic quadrilaterals is a problem that, again, we've talked about before. Yeah. And it starts with a 9-dot circle, and we encourage students to, oops.
I think if you're patient and let it load.
Okay. So in this problem, we're going to ask students to, oops. Sorry, I'm going to refresh.
Yeah, refresh. Yeah. Nice.
Okay. Draw a quadrilateral along, by joining 4 points along the edge of the circle, and ask them to work out the angles of the quadrilateral. And the reason we've chosen 9 points is that 360 degrees can be divided by 9 very easily. And so they can work out that this angle here is 40 degrees. Yeah. And this one will be 80 degrees. And these two will be 120 degrees. And once they know those angles, they can work out the missing angles in their isosceles triangles. And when they add the angles that are opposite to each other, they find the angles are up to 180 degrees. And there's some follow-up work which encourages them to see whether this also happens with 10-dot circles and 12-dot circles and so on. And they find that that also happens. Right. And they might suggest, well, this only happens because 9, 10, 12, 15, and 18 are all factors of 360. And why didn't I choose 7 dots and 11 dots? But this leads to the need to prove that the opposite angles of cyclic quadrilaterals are always 180 degrees. And we have an image here of a quadrilateral where the dots appear quite randomly. And the challenge is to get students to try and use the information in that image to figure out how they can prove that the opposite angles are up to 180 degrees. So as a last challenge for you, actually, we're running out of time.
I'll leave it.
Shall we?
Yeah, that's fine.
Okay, we'll give you a minute very quickly. Apologies that we've overrun. Can you use the information in that image to work out how you would convince yourself that the angles on a cyclic quadrilateral add up to 180 degrees? Shall we give the game away?
I don't know. Shall we give the game away, or shall we let people think about it?
Well, I'll kick off. I'll start.
Oh, yeah, start and then maybe stop.
So I'd be doing this with students who know that the angles in a quadrilateral add up to 360 degrees, and that and so in this quadrilateral we've got 2 red angles, 2 yellow angles, 2 purple angles, and 2 blue angles. So 2 red, 2 yellow, 2 purple, 2 blues add up to 360 degrees, or 2 X's and 2 Y's and 2 Z's and 2 W's add up to 360 degrees. But what happens when you add the opposite, when you look at the opposite angles? What do you notice about the opposite angles? Now, we rushed through this problem, and of course, in a class, working on 9 dot circles and then 10 and 12 feet might take up 1 or 2 lessons.
Yes.
So we're just visiting the very end of that journey.
Yeah.
But I hope it gives, like in tilted squares, the proof would come at the very end of that journey.
Yeah.
But hope it gives a feel for what one could do at the end after the exploring, the conjecturing, the generalizing, the visualizing.
Absolutely. Yeah. So
okay.
I think we are coming, well, apologies for overrunning. Let's just remind you, if we go back to the secondary teacher homepage, then we can just remind you, those of you who perhaps haven't been to any of our webinars before, or perhaps didn't know that they existed. As Charlie says, the Developing Mathematical Thinking section or what we've been focusing on most recently. And for example, if I wanted to catch up on the exploring and noticing, if I click on there, I have some guidance which we've written, and in that guidance we have got the recordings of those webinars, so do visit those. And so similarly, we will be embedding the recordings from today into the guidance for reasoning, convincing and proving. So don't forget that we started off from the mapping document. All the tasks here are linked to the curriculum, but also give you all those opportunities to reason. And finally, we would very much please appreciate your feedback. I'm going to pop a link to a Google form in the chat. If you could fill that in, we'd be very appreciative, because it means we can give our funders feedback as well. You may be interested to know that our next secondary teacher webinar is on the 12th of March. We're going to be focusing on developing, sort of nurturing curiosity, students' curiosity. Thank you ever so much for your participation on the chat. Charlie, any parting words?
No, you've covered everything that we wanted to.
Thank you, and we hope to see you again at a future webinar.